Hi, welcome to this lesson on Euclidean geometry, similarity and congruency. Let's have a look at similarity in polygons. So we will start off with the definition, and we say that two polygons, which I'll denote by P, A1, A2 up to AN, and Q, which is denoted by B1, B2 to Bn. So these AI and Bi, each letters represent the vertices of the polygon. And for example, A1, A2 would be one of the edges of that polygon. So P and Q are similar to each other, and we denote it by P with these three vertical lines, Q, if and only if all the following conditions are satisfied. Okay, so condition one is that all corresponding angles are equal. So that means if you're looking at a polygon, if you look at angle A1, then there must be some correspondence to another angle in the polygon Q, say B1, A2 equal B2, and so on. So in the order that we write them, those angles must be equal to each other. So it's important in the order that we write them. As well as all corresponding sides are in the same proportion. That means if I look at the edge A1, A2 and the edge B1, B2 in the polygon, and I take the ratio of those two, then that must be in the same proportion as A2, A3 to B2, B3, and so on up to the final edge of each polygon. So mathematically, this tells us that two polygons in the plane are similar if and only if they are equiangular, which means that for all corresponding vertices, the angles that are contained between them are equal, and the ratio of the corresponding sides of each shape are in the same proportion. Okay, so these two conditions must be satisfied for similarity between polygons. Let's have a look at an example. So if we look at this polygon ABCDEF and polygon PQRSTU, so this is a six-sided polygon for each, right? So we call these polygons hexagons, but they are irregular hexagons because, as you can see, all the angles and side lengths are differing from each other in each hexagon. So a regular hexagon is a hexagon where all six sides are equal and all interior angles are equal. Okay, but in this case, you can see that these two polygons, these two hexagonal polygons are irregular, but we need to check if they are similar to each other. So what we can do is we can look for some sort of direct correspondence. So I see angle A is 120 degrees and I see angle U is 120 degrees. And then if I read clockwise on this blue hexagonal polygon, the next angle is 105 and the next angle is 105. 135, 135, 87, 87, 108, 108, 165, and 165 degrees. Okay, and then also, so that means they are equiangular. So that means every angle in the one polygon is equal to the other angle in the other polygon. Okay, so we've established that case one is true, but then case two is that if we take the ratio of those corresponding sides, they must be equal. So the order in which we took the vertices, so AB and UP, if we divide those two out, so AB is 3 units, right? And UP was 4.5 units. So we have 3 divided by 4.5. But what is that? 3 divided by 4.5, that gives us 2 over 3. And then if I look at BC over PQ, so keeping in that order, right? So I read it as A, B, C, D, E, F, and I'm reading the other one as UP, Q, R, S, T. Okay, so we've seen that AP divided by UP gives us 2 over 3. Then what about BC over PQ? So BC was 4 units divided by PQ, which was 6 units, and 4 divided by 6 reduces to 2 over 3. So you can check, you just keep moving along the line. Then you check CD divided by QR and so on, and they should all give you the same proportion, which is 2 over 3. Hence, we say that the two polygons are similar, and we write it as ABCDEF is similar to UPQRST. And again, for emphasis, we need to write it in this precise order, as this notation will show us which angles are equal and what sides are in proportion to each other. So it's important that we write it in the correct order. So we can see that the red irregular hexagon essentially is a scaled up version of the blue hexagon by a factor of 3 over 2, right? So the blue hexagon, if it was increased by a factor of 3 over 2 everywhere, it would become the red hexagon. Or vice versa, the blue hexagon is a scaled down version of the red hexagon by a factor of 2 over 3, and that's the ratio we saw here. Okay, because we did the blue over the red, which is the smaller over the bigger, hence we got a smaller ratio 2 over 3. Whereas if we did the big over the small, we would have 3 over 2, which is a bigger ratio. All right, so essentially what happens with similarity in polygons is we need to check a specific order of the polygon and check that each of those angles are equal to each other, the corresponding angles that we've written it in that order, and the corresponding sides are all in the same proportion. All right, so that is similarity in polygons. I'll see you in the next one.